Be doing some reading as opposed to me lecturing my way through this. But our next topic is macromolecules. Macromolecules are hugely important, and you see the four listed over here: proteins, carbohydrates, lipids, and nucleic acids. You'll be reading more about those in your book as part of this week's work. But in this brief video, we'll talk a little bit about what organic compounds are and the key element associated with them. Why are macromolecules like those listed to the right so important, and what are the important things you should really be focusing on with these particular molecules? Let's start with this idea that carbon is a very versatile element. It is the key to macromolecules. So let's back up for a second. When we talk about macromolecules, macro, as you can read from the name here, macro means large molecules. So these are going to be large molecules that we associate particularly with life. Whenever you hear the term organic chemistry, we're talking about things, molecules, that are based in this element, carbon. Why carbon? Why is carbon so critical to the molecules that we think of as being important for life? You see some reasons here. I listed them on this group, but don't focus on them too hard. Carbon doesn't lose electrons. Why does it not lose electrons? It goes back to that same statement we looked at before. It is due to the arrangement and number of electrons. Carbon has somewhat unique properties. So, since carbon never loses electrons, it instead makes a lot of bonds with other elements. So you see down here, for example, we have methane because carbon is making a bond here, and a bond here, and a bond there, and a bond there. These are covalent bonds because we're sharing electrons, and therefore we have methane. So carbon, the term we have for this is tetravalent. Carbon has 4 electrons that it likes to share with other elements. So that's why carbon is tetravalent. But it can also make these long chains. We refer to something called the carbon skeleton. Look at all the carbons all attached here in a row. That is an important characteristic of carbon, that it can make these rather complex molecules. And it can also make these rings. You see these ring shapes here. Carbon can form rings and double bonds and triple bonds. Therefore, carbon is really important, and it is critical to forming the 4 macromolecules that we'll be learning about in this section here. Before you read about macromolecules, I just wanted to remind you again of this term organic. Organic refers to molecules that are carbon-based. So all the ones you're going to read about in your book regarding the macromolecules are organic molecules. They're all carbon-based. And the only part that I'll talk about, because it's not really in your book very much, is this idea of what's called monomers to polymers. All of the macromolecules you'll be reading about, carbohydrates, lipids, proteins, nucleic acids, those are the polymers. Those are the big molecules. Well, those are all made of small building block molecules. Here's just an example of one. You see a monosaccharide, a simple sugar, plus a monosaccharide and a simple sugar in the presence of enzymes will make a bond, and we will get a disaccharide. That is a larger molecule. We can produce polysaccharides in the exact same way. So whenever you see monomers to polymers, it's how we make large molecules. A polysaccharide is another term for a sugar, a carbohydrate. So this is going to be true for the carbohydrates. The very similar thing happens to make proteins. The very similar thing happens to make lipids and nucleic acids. So they all work in a very similar way. If you combine the small building block pieces, like these simple sugars, you make a bigger sugar. You take simple pieces of proteins called amino acids and put them together, then you will get a protein. So that's just a basic idea that I want you to think about, that all of the big molecules have small parts that make them up. So, as you read about macromolecules in your book, I want you to focus on these areas. What are their monomers? I've already mentioned a couple, but what are the monomers? What makes them up? What are the building blocks to each of the macromolecules? Some of them have alternate names. Think about those. What does each macromolecule class do? Why do we need carbohydrates? Why do we need lipids? And where do we find these in the body? What chemically distinguishes it? That is, what makes that macromolecule unique? What's special about carbohydrates, or what's special about proteins or nucleic acids? So that's what I want you to think about as you do your reading, and your reading is listed on the Blackboard site. That's why I gave you a couple of examples of why we care about these macromolecules. Let me move me out of the way here. A couple of examples of why we care. From a medical perspective, we care about the lipoproteins. Lipids and proteins can combine to form lipoproteins. Why do we care about macromolecules? Why do you care about chemistry in the healthcare field? Well, in this case, you may have heard of LDLs and HDLs, low-density lipoproteins, LDLs. These are the ones that we associate with a blockage of arteries. These are bad. These are the ones that are going to increase the risk of a cardiovascular event. HDLs, which are also part of our cholesterol group, are good because they carry lipids to the liver to be metabolized. So that's just one example of why we might care. Maybe you need a little different example. Maybe you can relate to this one a little easier. When we think about food, food is actually, well, I'll back up. When we talk about the macromolecules make up our food. So a Whopper or a Coke or salad or whatever is made of combinations of sugars and lipids and proteins. Just to give you an example of what we talk about, and we'll get to this more in A&P 2, but what unit of energy do we put on a food label to tell us how much energy is in there? We say how many calories are in there. So a Coke, for example, a Coke of this size is going to have 240 calories. Why does it have calories? Because it has lots of mostly sugars in it, mostly carbohydrates. A Whopper has 660 calories in it. If you wanted to eat a Whopper and then burn off those calories, because there's so much energy in a Whopper, so many calories in a Whopper, you would have to walk for 3 hours to burn off that many calories, or you'd have to jog for 75 minutes to burn off that many calories. So I'll leave you with the thought that not only do we care about macromolecules from their biologic perspective, but they're also a measure, or they are how we burn them rather, for our energy. So with that, again, I direct you to the website so you can have a look at your reading on macromolecules.